Let's start by introducing containers. In this video, you'll learn about the key features of containers and the advantages of using containers for application deployment compared to alternatives such as deploying apps directly to virtual machines. You'll learn about Google's Cloud Build, and then you can see how you can use it to build and manage your application images. So now, not very long ago, the default way to deploy an application was on its own physical computer. To set one up, you'd find some physical space, power, cooling, network connectivity for it, and then install an operating system, any software dependencies, and then finally the application itself. And if you need more processing power, redundancy, security, or scalability, what'd you do? Well, you'd have to simply add more computers. It was very common for each computer to have a single purpose, for example, a database, web server, or content delivery. This practice, as you might imagine, wasted resources, and it took a lot of time to deploy, maintain, and scale. It also wasn't very portable at all. Applications were built for a specific operating system, and sometimes even for specific hardware as well. In comes the dawn of virtualization. Virtualization helped by making it possible to run multiple virtual servers and operating systems on the same physical computer. A hypervisor is the software layer that breaks the dependencies of an operating system with its underlying hardware and allows several virtual machines to share that same hardware. KVM is one well-known hypervisor. Today, you can use virtualization to deploy new servers fairly quickly. Now, adopting virtualization means that it takes us less time to deploy new solutions. We waste less of the resources on those physical computers that we're using. And we get some improved portability because virtual machines can be imaged and then moved around. However, the application, all of its dependencies and operating system are still bundled together. And it's not very easy to move from a VM from one hypervisor product to another. And every time you start up a VM, its operating system still takes time to boot up. Running multiple applications within a single VM also creates another tricky problem. Applications that share dependencies are not isolated from each other. The resource requirements from one application can starve out other applications of the resources that they need. Also, a dependency upgrade for one application might cause another to simply stop working. You can try to solve this problem with rigorous software engineering policies. For example, you could lock down the dependencies so that no application is allowed to make changes, but this leads to new problems because dependencies do need to be upgraded occasionally. You can add integration tests to ensure that applications work. Integration tests are great, but dependency problems can cause new failure modes that are hard to troubleshoot. And it really slows down development if you have to rely on integration tests to simply just perform basic integrity checks of your application environment. Now, the VM-centric way to solve this problem is to run a dedicated virtual machine for each application. Each application maintains its own dependencies, and the kernel is isolated, so one application won't affect the performance of another. And what you can get, as you can see here, is two complete copies of the kernel that are running. But here too we can run into issues, as you're probably thinking. Scale this approach to hundreds of thousands of applications, and you can quickly see the limitation. Just imagine trying to do a simple kernel update. So, for large systems, dedicated VMs are redundant and wasteful. VMs are also relatively slow to start up because the entire operating system has to boot. A more efficient way to resolve the dependency problem is to implement abstraction at the level of the application and its dependencies. You don't have to virtualize the entire machine or even the entire operating system, but just the user space. And again, the user space is all of the code that resides above the kernel, and it includes the applications and their dependencies. This is what it means to create containers. Containers are isolated user spaces for running application code. Containers are lightweight because they don't carry a full operating system. They can be scheduled or packed tightly onto the underlying system, which is very efficient. They can be created and shut down very quickly because you're just starting and stopping the processes that make up the application and not booting up an entire VM and initializing an operating system for each application. Developers appreciate this level of abstraction because they don't want to worry about the rest of the system. Containerization is the next step in the evolution of managing code. You now understand containers as delivery vehicles for application code. They're lightweight, standalone, resource-efficient, portable execution packages. You develop application code in the usual way, on desktops, laptops, and servers. The container allows you to execute your final code on VMs without worrying about software dependencies like application runtimes, system tools, system libraries, and other settings. You package your code with all the dependencies it needs, and the engine that executes your container is responsible for making them available at runtime. Containers appeal to developers because they're an application-centric way to deliver high-performing and scalable applications. Containers also allow developers to safely make assumptions about the underlying hardware and software. With a Linux kernel underneath, you no longer have code that works on your laptop but doesn't work in production. The container is the same and runs the same anywhere. If you make incremental changes to a container based on a production image, you can deploy it very quickly with a single file copy. This speeds up your development process. Finally, containers make it easier to build applications that use the microservices design pattern, that is, loosely coupled, fine-grained components. This modular design pattern allows the operating system to scale and also upgrade components of an application without affecting the application as a whole.